So today I'm going to talk about quantum means the minimum circuit size problem. And this is a joint work with Jin Zhou from Harvard University, Ray Zhezhen from UT Austin, and Jai Zhang from Boston University. And I think he moves to Caltech right now. So let me start from defining the minimum circuit size problem. So because I expect like most of the audience here are not from theoretical computer science community. So let me try to like slowly define it, and then we can go to see like why this problem could be very important in quantum computing. So the minimum circuit size problem is as follows. So you are given input. The input is a truth table of a Boolean function. So you can just consider a function which has a binary string of length n. And it maps a binary string of length n to either 0 or 1. So you can consider it as like an ordinary decisional problem, like set or three sum or any computational problems you can imagine. And you are also given one t. So you are given actually it's given a number t in the unary form. And the question is also very simple. The question is asking you to output if there exists a classical circuit, they can compute f by using at most t gates. So t is given in a unary form here. And of course, the gate say in the classical setting you consider can be and or not. So let me try to visualize the problem. So you are given a truth table. This truth table have 2 to the n entries, like f0 to the n, f0 to the n minus 1 with another 1, and f0 to the n minus 2, 1, 0, and so on to like 0, 1. So note that the input size of this problem is already 2 to the n. So an efficient algorithm for MCSP runs in time wholly in 2 to the n. Okay, because like when we are talking about a symptotic notion, we actually consider if it is polynomial in the input size or exponential in the input size. So now because we make the input size to be 2 to the n, so when we want to say a polynomial time algorithm, actually it is polynomial in 2 to the n. So you can also write it as 2 to the bigger O n. Okay, and know that when t is small, like smaller than log n, then this problem is in P, you can just brute force search like all possible circuits. Okay, any question about the problem definition? So this is a classical MCSP, and then later we will see like how do we generalize this problem to a quantum setting, like quantum inputs, and also consider quantum circuit complexity and so on. Yeah.
Oh, okay. And one thing. Oh, sorry.
Yeah,
oh,
yeah,
you
sure.
You go first.
No, you can go first. I just want to say something random. Yeah.
Okay, so it's just a small question. So, here it's a decide.
It's a decision problem.
Yeah, it's a decision problem. So we don't need to produce the circuit. We just have to say, oh, there exists.
Exactly.
Okay.
Yeah.
Yeah. Thank you.
And this is also a very good question because like this decision problem is already hard. Actually, we will see later. And actually its search problem could be even harder. So yeah, we will see some connections later. Yeah, but just keep in mind, right now we only need to decide whether there exists a circuit that can use like at most T gates or not. And yeah. Okay, so let me go to the next slide. So actually this problem is very interesting because MCSP is an NP intermediate problem, which means that it seems that it is not NP complete, or like some people don't believe it is NP complete, but we don't have an efficient algorithm for this problem too, either, sorry. So the first fact is that it is an NP intermediate problem, and also MCSP is in NP because we can find a certificate to prove that to verify that a given Boolean function has a small circuit or not. And actually, the certificate is the circuit, and the verifier just checks all the 2 to the n inputs. And also, there is a very important conjecture which is called parabolic conjecture, which says that MCSP the best algorithm for MCSP is brute force search. Like you need to enumerate all the possible circuits with size at the most t, and then after you running all the circuits, you can decide whether which circuit can compute the target function f. So this is called the parabolic conjecture, and this conjecture has been made in 1950. So you can see that MCSP is a problem probably with age like 70 or 80-year-old. And actually, Levin, like Cook Levin, when he wrote his paper about like NP completeness or the NP hardness, actually he also wants to show that MCSP is NP complete. So I have heard some gossip say that because of this problem, he delayed to publish that paper for like a few months. So this paper is in 1973, and actually many people, including Levin, believe that MCSP should be NP complete. Okay, and we also found that many variants of MCSP are NP complete. Like if you just consider partial function, not total functions, or like sparse MCSP or multi-output MCSP, all of them are NP complete. But the standard MCSP, we don't know right now. Okay, and actually these are very recent results. On the other hand, some other people believe that MCSP could be in P. So, but there are some evidence showing that probably this is not, and showing that okay, solving MCSP efficiently implies break one-way functions. So, like if you move MCSP to P, that will give you some like very bad things, like there will be no one-way function. This implies that you don't have cryptography. Public key cryptography anymore. So it's interesting. This problem, if you can prove its hardness, it gives you many important implications, like in crypto or in other areas, or say like some interesting things happens. Yeah, we will see more of them later. But any questions about this slide, like the hardness of MCSP? No, then we can go to the next slide. So as I said, this problem connects many other problems in TCS. Like if you can prove its hardness, then you can show some interesting things in crypto. And if you can prove its hardness or showing that this problem is easy, then you can have some applications to prove circuit lower bound. Now you can also have like some equivalence relationship between learning algorithm and the MCSP. Also here, the learning algorithm, here I mean pack learning. And of course, you can have more applications when proving the hardness of MCSP. So here I just like list some interesting facts. For example, if you can prove that MCSP has a polynomial time algorithm, then you can show that there doesn't exist pseudo-random generator, and there is no one-way function. Then there's no public key cryptography. And another thing is that if there exists IO, which is another crypto primitive, then MCSP could be as hard as set, which is an NP complete problem. And also, if you can prove that MCSP has a polynomial time algorithm, then all polynomial size Boolean function can be pack learned in probabilistic polynomial time. And also, if you can show a reduction from set to MCSP, then you can prove some interesting circuit lower bound, like EXP is not in P over poly, or EXP is not equal to ZPP. So those are like very interesting results in complexity theory. Oops, wait. Yeah. So that's what I want to say about the classical MCSP. Its hardness is mysterious, not in P, not in co-NP intersect NP, also not NP complete, and no algorithm better than brute force search for this problem. And also there is no search to decision reduction. So as David mentioned like a few slides ago, saying that why don't we consider search version of MCSP? And actually, if it is NP complete problem, all NP complete problem have a search version to decision version reduction. But for this problem, we haven't had a search to decision reduction yet. So that's another very interesting fact right now. And also this problem has many applications to other problems like learning, crypto, and circuit complexity. However, we know that in the classical setting, in MCSP, we only study classical circuit complexity for classical objects, like just Boolean functions. So why don't we consider quantum circuit complexity and the quantum objects? And also, like you see here, all MCSP problem, when we say it is easy or it is hard, we are talking about whether there exists a classical algorithm for it. Why don't we consider quantum algorithm for MCSP? So there's another problem we can consider. And also you can consider quantum reduction to prove its hardness and so on. So actually, when you try to move MCSP to a quantum setting, actually there are many dimensions you need to consider, like the target, the quantum circuit complexity, the quantum algorithm, and also the quantum reductions. And in this work, actually, we try to initiate the study of quantum version of MCSP in all these 4 dimensions. Actually, we don't have much result for quantum reductions, but we do have several interesting results for quantum circuit complexity, quantum objects, and quantum algorithms. Okay, so that's our goal. So in this work, actually, we define 3 different quantum MCSP problems. The first one is very close to a classical one. We are still given the truth table T of a Boolean function and some integer. Oh, sorry. The integer is also given in the unary form, like T ones. Okay. And we are output circuit that can compute F by using at most T gates. Sorry, here it is still a decision problem, but because I want to put everything in one slide, so it looks like a search problem. But here I'm talking about the decision problem, which is to decide if there's a quantum circuit that can compute F by using at most T gates. Okay. And for unitary, we also define a unitary minimum quantum circuit size problem. So for this problem, we change the target. We change the target to from the Boolean function to a unitary. Okay, and the question is that whether we can compute the quantum circuit complexity of this unitary. And also we are considering the decision problem first. And we also consider a state version of the minimum quantum circuit size problem. So for a state version, we are given a vector of n qubit state. Like for each state, for n qubit state, you can write it as a 2 to the n vector, 2 to the n elements vector. And this is one input setting. And another input setting is that actually, because you know that in the quantum setting, it is not how to say, not practical to have a classical description of a quantum state. So actually, you can also have access to arbitrary many copies of this quantum state. Like you have a pool, and you have many quantum states there. And when you want to use it, you just get one from the pool. Okay, and you are also given the n and the t. And the question is that whether there is a quantum circuit that can compute this quantum state by using at most T gates. Okay, so these are the 3 main problems we are considering in this paper. So any questions about these 3 problems or like anything else about quantum MCSP?
So are you going to mention which one will be difficult, like whether there is a reduction from one to the other?
Yeah, so actually, okay, I can say this first. So the first one, the MCSP problem, I think this problem is slightly easier because we find a reduction from this one to the second one, the unitary MCSP. But except for that reduction, we don't know any other reductions between them. Like this, the state version of MCSP is actually a little bit mysterious. Like I cannot see any connection to these two. Okay, but for sure, I think unitary one is harder than the Boolean function one. Okay, for state one, I don't know, but actually all three problems are hard because like actually we cannot prove that they are in MP. So we will see this fact soon. And we also have some results. Probably you can see probably these two problems are slightly harder than the first problem. Yeah, we will go to there later. Yeah, very good question. Any other question?
Thanks.
Yes, I have one question.
Okay, good.
Like here you say to compute, what does it mean? Like in the state minima quantum circuit, to compute the state sign, I would imagine like the the initial state is O0 and the final state is state S. But to compute U and compute F, I'm a little bit confused. Like how do I compute U?
Oh, yeah. So for compute U, which just means that you have a quantum circuit, and that quantum circuit can be represented by another unitary, right? So you just consider, okay, if that unitary is close to the given unitary. So you can just consider like the two known distance or the diamond known distance or something. But here I think we consider what we consider is a two known distance between the U of the quantum circuit and the target function, the target unitary U. So like the matrix distance. Yeah. Is that clear?
Yes. Then I just wonder like if how do I do this in like maybe like in IDNQ I mean like I compose some operations, but then I just to compare these operations with the target U like this.
Yeah, so there are several ways to do that. The first thing is that for each quantum gate, you can write it as a unitary, right? And then you just append with identity, and then you times all the unitary together, then you come out with a big unitary. And just compare whether this big unitary is close to the target unitary. That's one possible way. And another possible way is that you are given the target unitary and you know the quantum the gate. You can compute the unitary by applying the gate, right? The inverse of the gate. And then if it comes to something close to identity, then you can say, okay, the quantum circuit should be close to the unitary. Yeah, that's another way to do it.
And so to find the U, I using some classical computer to do this. Then I check on maybe quantum computer. Is it like this?
That's a good question. So there are two ways. The first one is what I just said, like you just classically compute the unitary. So this can be done by classical computer. But to prove something else, because that approach is not very efficient, you need to like write down everything about the unitary. And sometimes it is inefficient. And another way is that you can just check the quantum circuit, whether the quantum circuit and the target unitary U, they are consistent with many quantum states. That you can try all the computational basis state and the Hadamard based state. If you check all of them are close, then you can prove that actually these two unitary are close. That's another way to verify it.
Okay, thank you.
Yeah, no problem.
Oh, hello. Okay,
hello.
I have one more question. So
yeah,
So from the discussion, it sounds like, oh, there are a lot of approximation thing that's going on. So there are different ways to take approximation. And so
yeah,
one question I have is that, okay, in this quantum setting, often we have to, in this quantum setting, we often have to do with some probabilistic thing. So the analogy in classical, it seems like more of more like, okay, we want to approximate the function. And as long as as long as the difference is small enough, we're okay. Okay, so more precisely, my question is, the classical version of the analogy of these problems that you're saying would be slightly different from the thing you presented. And so I wonder, is there a big difference in these two questions? Do you kind of see what I'm saying?
You say what's the difference between classical and the quantum in terms of like?
Okay.
So
both are classical, but one is more of an approximated form. So for example, the original classical question is, okay, can I construct a circuit that computes the function? But the approximate version would be that, can I construct a circuit that approximately computes the function?
Yes.
Okay,
yeah.
And
so
is there a big difference between these two problems?
Yeah, there's a difference. I think there are many variants when you consider error in the classical setting, that they have a gap version or they have an approximation version. The gap version means that probably you just not consider S or, T, or you just consider a single T. You consider a T and a T prime, and you want to say whether a circuit is above T or smaller than T prime, something like that. Or say, because classically you don't have a random circuit, so you are not considering random outputs. So yeah, classically you can consider this kind of approximation, but not in terms of random circuit, like, because your output is not random. The classical circuit don't have a random output. So that's one thing. And another thing is that, yeah, your question is very important. Like in the quantum setting, actually you can see that the quantum circuit outputs can have error, and actually quantum circuits are inherently random, right? So when you define the problem in a quantum setting, actually you need to define the problem in a right way, not just like here. We just define it as a decision problem, and we don't give any error or something here. So actually, this is not a formal definition, because just for ease of presentation, I didn't put like the error or something here. But to deal with the error and the probability issue, you need to define it as something we call promise problem. And you also need to consider that the input is not always good. You need to consider, okay, sometimes we cannot decide whether there is the number of gates or something. So yeah, that's a very important question, and we try to handle this issue. We spend lots of time to handle this issue in our paper, actually. Yeah.
I see. Okay, cool.
Yeah. Thank you.
Sorry, I just have some definition question. So
yeah, good.
What's the difference of all the input T in three problems? It looks like in the first Boolean problem, you are given the function and you decide the T, whether larger T you can compute it or not. And for the unitary, I'm not sure what's the one T is identity T or.
Oh, yeah. So here the T, so here this should also be 1 to the T. So actually 1 to the T just means that you are given like T ones, okay? Like you are given like 1, 1, 1, and there are T ones there. So this is just like a standard trick in computer science to make the problem size to be like good. Okay, so actually here you can just consider this one to be T. Like you are just given T, and then you try to decide where there are at most T gates. But because like when we define a problem, we need to define it in a good way. So we say it is 1 to the T to make the problem size accurate. Yeah. It's a very like so it's a very subtle issue. Like if you just give T here, when you consider polynomial time algorithm for this problem, they may give you some like not very good phenomenon to analyze. So yeah, you can just consider 1 to the T here to be T, the integer T, and just want to decide whether there are T gates or not.
Okay. Okay. Thank you.
No problem. Okay, so I think we can continue. So we start from the Boolean version of minimum quantum circuit size problem. Yeah, I will also mention like these two problems later, but I think we will not go to the details of these two problems. So let me just tell you some like challenges, difficulties, or advantage when we want to do quantization of like these problems. So first, quantum computing, I think as someone just said, that quantum computing is generally random and erroneous. So when you want to define this problem, you cannot just define it as a decision problem like in this form. You need to define it as a promise problem. And also, quantum circuits are reversible. Like we know that classical Boolean circuits, you cannot revert it. But quantum circuits are reversible, and actually based on this reversible property, you can design search to decision reduction or self-reductions for the unitary version and the state version MCSP. And actually, search to decision reduction and the self-reduction for MCSP in the classical setting is a long-standing open problem. And but in MCSP and the SMCSP, we can prove that okay, this reduction exists. And for the ancilla qubits, so it is another interesting phenomenon in the quantum setting, because when you have more ancillas, you can use your circuit can use these ancillas to compute the unitary or say the functions, right? But when you want to represent this circuit, you may need to use the matrix will be much larger than the classical the matrix we have in the classical setting. So actually, the introduction of ancilla qubits make the problem harder. So because of the ancilla qubits, the problem goes from MP to QCMA. So QCMA is a quantum analogous of MP, which is a larger class than MP. So actually, this problem is not, we don't know if it is in MP. Actually, we don't know how to prove it is in MP, but this problem is in QCMA. So this problem seems to be harder than the classical MCSP problem. And also, the final thing is that when we consider quantum circuit, actually you may consider different universal gate states like Hadamard plus Toffoli, or like single qubit rotation plus D0, or some other gate states. Actually, different gate states may introduce different properties, and we found that certain results only hold for particular gate states. So that's another interesting phenomenon in the quantum setting, because classically you just consider N or N not, or just NAND, something like that. But in the quantum setting, you need to consider lots of different cases. Yeah. So that's the three interesting facts we found when we study the quantum version of MCSP problem. And most of our results are from like these three observations. Okay. So let's start from talking about the hardness of this problem. So as I said, this problem, MQCSP, the first guess is that this problem is in MP, okay, and it is not MP complete, and we may conjecture that it is not in BQP, okay. But when you give a second thought, then you want to ask, is this problem really in MP? And also, can we give some condition or conditional lower bound for this problem? Like, can we say this problem is some other problem hard, like another complexity class which is in MP but not in BQP? Or can we say that if MQCSP is in BQP, like from here to here, then some bad things will happen, like the no quantum secure one-way function and so on. Okay. So let's start from the whether the question like if MQCSP is in MP. So now suppose F has quantum circuit of size at most T. Okay, then we let C be the quantum circuit that computes F without using any ancilla qubits. So this is the quantum circuit that can compute the, by the way, do everyone know the definition of MP? Like probably I just quickly go through it. So the definition of MP, is that if the instance, like the input function, has a small depth, sorry, has a quantum circuit with size at most t, then the prover should be able to give a certificate to show that, okay, this function has a quantum circuit of size at most t. So actually, that certificate is the circuit C. Okay, and actually this is how classical MCSP being proved to have to be in the MP. Okay, so here we follow the same idea, right? We make the certificate to be the circuit C here. So with that, the prover send the circuit C to the verifier, and then the verifier just need to check whether F and C. Yeah, I forgot to mention that. Okay, but here, when the verifier get the quantum circuit C, it cannot run the C on the input, since it only has classical part. Because for MP, we only consider classical verifier. So he is given a quantum circuit C, but he cannot run the he cannot run the circuit. So that's a problem. So how does the verifier compute it? However, since remember that for the MCSP or MQCSP problem, we allow V to run in 2 to the big O n time, because like the input size of the problem is 2 to the n. So a polynomial verifier is actually allowed to run 2 to the big O n time. So the verifier simply compute the circuit. Okay, he simply compute the unitary for the circuit. So given C, you can just compute its unitary. So it is a 2 to the n by 2 to the n large matrix, but it's still okay because we allow to use 2 to the big O n time to do a verification. So after he compute the unitary, so we can check if unitary of C is consistent with F, so the problem is still in MP. So he just try all the computational basis and do a matrix product, right? And then try to say, okay, if U and this C are consistent for all X. Okay, so that's the first idea to prove that MQCSP is in MP. Yeah, so any question about like this verification procedure? No? So yeah, I think this one is not, it's not very hard if you know like MP or something. So it's just very simple, like you just give the quantum circuit, and you don't need to run a quantum circuit, you just compute the unitary of that quantum circuit and then try to see whether that unitary is consistent with the target unitary. Okay, oh sorry, the target function F. I make something wrong. Yeah, the target function F. Yeah. Okay, but now the question is that what if we allow a polynomial NCR qubit? So here you see that we only allow, so here we only consider the input. Okay, but for general quantum computation, actually you will use lots of NCR qubits to your circuit. So now you will have polynomial many qubits, say like n squared qubits. Okay. Actually, in this case, you will have the unitary of this circuit will not be polynomial in 2 to the n, because like, for example, if here you have n squared NCR qubits, then you will have 2 to the n squared times 2 to the n squared elements. It is not polynomial in 2 to the n. Okay, so now if you still follow the same approach, this approach takes time, 2 to the poly n, to compute a unitary matrix of C, which is not efficient anymore. Okay. So now the problem goes from MP to out of MP. Okay. So that's why we say like when you introduce the NCR qubits to quantum circuit, this problem becomes harder. It goes from the original like MP to like to other complexity class. And actually, it is not end of the world, because we can put it into another complexity class called QCMA. Okay. So The idea is even simpler when you consider QCMA, because in QCMA, it is very similar to MP, but with quantum efficient verifier. Okay. So which means that here, the verifier can run quantum algorithm. So in this case, P gives V the quantum circuit, then V, it doesn't try to transfer the circuit into a big unitary. It just run the quantum circuit on all the computational input X. Okay. So he runs C on all X and 0 on Epsilon, and then check if it is consistent with the Boolean function. Okay. So let me try to make this conclusion. When there are too many NCR qubits, then the problem goes from MP to QCMA. So that's the conclusion here. Yeah. So any questions about like the hardness of MCSP? The MQCSP, like MP and the QCMA. Okay, no, then we can go to next slide.
Sorry.
Yeah.
Just like question, is there any intuitive way to understand why the NCR qubit will change their class?
Yeah. Let me try to go through it again. So, so the original approach is that when you just have n qubits, then you can represent your circuit as a 2 to the n by 2 to the n unitary, right? So this matrix, the size of this matrix is 2 to the 2n. Okay, and 2 to the 2n is still like 2 to the big O n. Note that for the verifier, you're only allowed to use like 2 to the big O n time, and 2 to the 2n is fine because it is still 2 to the big O n. So, but if you allow ancillar qubits, the corresponding unitary will have 2 to the poly m times 2 to the poly n unitary. Okay, so 2 to the poly n is nothing is much larger than 2 to the big O n. So the main point is that the verification procedure we considered before is not efficient anymore. Okay. Does that make sense to you? Because we haven't been able to prove that it is not in MP, but we just said that, okay, the previous approach fails. Okay, you may be able to find another way to prove it is MP, but like the very straightforward approach doesn't work. Yeah.
Okay, I see.
Okay, good. So then let me go to considering the hardness of MQCSP and for like conditional and a conditional lower bound. Like we just talked about the upper bound. Like we say, okay, we can make this problem to be in QCMA. We prove that, okay, it cannot be too harder than QCMA. But we are considering the lower bound right now. We want to show, okay, to show whether this problem is in BQP or not in BQP, or if it is possible to be in MP or something, like where these problems are. Like now we don't know. We're saying probably it is on the boundary. Probably it can go to BQP, or it can just be an QCMA intermediate problem or QCMA complete problem. So the first thing is that we prove a conditional lower bound. We show that if MQCSP is in BQP, then there is no quantum secure one-way function. So this direction follows from the classical MCSP. Classically, MCSP can distinguish random function from a pseudo-random function. So the pseudo-random function f, so okay, probably I should define pseudo-random function. So pseudo-random function means that if you are given a truly random function and a function generated by some efficient procedure, you should not be able to distinguish these two functions if that procedure is a pseudo-random function procedure. Okay. So The pseudo-random function, because the pseudo-random function is generated by some efficient procedure, so it must have a small size circuit. So like a polynomial size quantum circuit that generate, or a classical circuit generate that function. But for a random function, it has a super polynomial size circuit on average. Like if you just randomly pick a function from all the functions, then that function must have super polynomial size circuit on average. So that's by some counting argument. So there's a classical result shown by Rasborov and Rudich in, I think, 1997, and it has been extended by Kai et al. In 2000. So actually, it follows from a standard crypto framework showing that if you have a one-way function, then you can use this one-way function to construct a pseudo-random generator. And then if you have a pseudo-random generator, you can use the GGN construction to construct a local pseudo-random generator H. Okay. And actually, so now you are given like the generator, which is the PRG construct from one-way function. So PRG is that if you have an MB random string, you can construct 2 MB random string, which is hard to distinguish from truly random string. Okay, so this is the GGN construction. I think we don't need to go through it. Yeah, probably I give too many details here. Okay, so here we fix K, and we can view like this construction as a truth table of some function. Okay.
Sorry, do you change your slide or not?
Oh wait, can you see?
Your slide didn't change.
Really? Let me try again. Oops. So can you still see my slides? Because I think I still link that.
Still see your slide. It is fixed.
Okay. Let me just go. Okay. Okay, good. I think you can see the changes right now, right?
Yes.
Okay. So now we have a PRG construct from one function, and then yeah, so we don't need to go through all the details, but the point is that you have this PRG. So this is a PRG that maps a small random string to a large random string. So you are given some small x, then you just use this to construct a large random string, and you just view this large random string as a truth table of some Boolean function. Okay, and then you use your MCSP oracle or say algorithm, like to check whether the given string has a small circuit complexity. Okay, because now the string represents certain Boolean function. So you can check it by using your MCSP oracle. Okay, so this gives you this result. Like if you have a efficient algorithm for MCSP, then there is no quantum secure one-way function. And actually, the main technical part is to prove that all these constructions are also quantum secure, or say it also holds in the quantum setting. But the main framework follows from the classical framework. Okay. Yeah, so that's why I said to prove this framework works, you need to show that like all these components are also holds in the quantum setting. Okay. So now, if you believe if you believe that there's quantum secure one-way function and the PRG, then you should believe that this problem is not in BQP, because if MCSP is in BQP, then you don't have this crypto primitive. Then you don't have any public crypto anymore. Yeah. Okay. So in this way, we can show a conditional result that, okay, this problem probably be either here or here. Okay. And actually for this problem, we prove some evidence. We show that actually this problem is in SDK hard. So SDK is another problem which is in MP, but not MP complete. Okay, it's kind of like here, it's larger than P. So it means that the hardest problem in SDK reduced to MQCSP. And we also show that if you consider multi output MQCSP, this problem is MP hard. And also this problem is lattice hard, which means that all lattice problems reduce to MQCSP and so on. And all this follows from modifying quantum results. Like we know that classical MCSP also have these results, and actually we show that all these results can be quantized to the quantum MCSP. Oops. Okay. Any questions about the MQCSP, like the Boolean function one? If there's no question, we will go to a unitary and a state version. Okay, so
is the K the same as T you defined before?
You mean the K here?
Yeah.
Sorry, no. This K is the key of the pseudo-random generator.
Okay.
Yeah,
And
so it's a random key.
in the previous slide, you have U-prime and you have defined previous slide. And what? No. Yeah, you not too much.
Yeah.
Yeah.
Okay.
So the K is also the key.
Yeah.
Okay.
Yeah.
Then why you have different? You multiply several G, or you just generate the DRG. Okay, thank you.
Yeah. Yeah. Sorry. Yeah. This because if I shouldn't put the whole GGN construction here because there are many notations that may confuse you. Yeah. Yeah, so actually the main idea is like very simple. So if you have a one-way function, then you can construct a pseudo-random generator PRG. And then now you just view the output of a PRG as the truth table of some Boolean function. Okay. And because you have a MCSP algorithm, you can use the algorithm to distinguish whether the output has a small circuit or not. And because we know that random function should random function should have a large circuit, and PRF, or say a Boolean function generated in this way has a polynomial size circuit. So MCSP can distinguish these two cases, so it can break the PRG, or say the pseudo random function. Okay, so let me go to the last part, which is the unitary minimum quantum circuit size problem and the state minimum quantum circuit size problem. And for these two problems, I will tell you like some interesting result and probably just some ideas like how to get them, but I'm not going to go to the technical details. So the first interesting thing we have for these two problems is that we can prove search to decision reduction for UMCSP and the SMCSP. So those are like search problem reduced to decision problems. And actually, these are not known for MCSP and the MQCSP. And we also have a stealth reduction for SMCSP. So which means that an n size problem reduced to an n-1 size problem. So for take this as an example. So you are given an n qubit state and an integer 1 to the t. Then we can prove if you can solve a problem with n-1 qubit state, then you can still solve the same problem. So that's called a self-reduction. And also this property is not known for MCSP, MQCSP, and even UMCSP. And actually you need to be aware that if it is an NP-complete problem, then they must have these two reductions. Like all NP-complete problems like set, subset sum, or any NP-complete problem need to have search decision reduction and the self-reduction. Oops. So that's too interesting about them. And how do we get the search decision reduction and self-reduction? The main idea is that because quantum circuits are reversible, right? So if you are given a unitary, and you can decide whether it has a circuit of size greater than t or smaller than t, the unitary have a size at most t. Then you just guess each gate, and then you apply the gate to a unitary to uncompute the gate. And then if you can decrease the t, then you make the right guess, and then you continue. Then you guess the next one and uncompute it from the unitary, and then you keep doing this. Then eventually you can find the circuit by just uncomputing the unitary. So, and we do have many applications for these problems. Like for unitary MCSP, as we said, we prove a gap. We show that gap MQCSP reduced to UMCSP. Okay, and this reduction generalizes many applications of MQCSP to UMCSP. Like if you can prove some hardness result for UMCSP, then you can also find hardness magnification, quantum circuit lower bound, and the breaking one-way function, and even learning algorithm. Yeah, so that's about UMCSP. And for SMCSP, because we don't know any connection from MCSP to UMCSP or the original MQCSP, so we can actually only show that something else. But actually, this problem, because that quantum state is a very interesting object in quantum information. Like people are trying to consider the state, the complexity of the state, or considering pseudo-random state, or considering how to learn the state, like shadow tomography or full state tomography. There are many topics about state. So actually, we show that if you can solve this SMCSP problem, then you can break quantum pseudo-random states, which is a quantum generalization of PRG. Oops. And then there's another interesting fact, which is this is a very wild topic. Actually, if you can solve the SMCSP, you can estimate the one-hole volume under ADS-CFT correspondence and the C equal to B conjecture. So those are something about quantum gravity. And yeah, if you can solve this problem, and if you believe lots of conjectures in gravity, then you can estimate the wormhole volume efficiently. And the last thing is about tomography. So if you can solve this problem, then you can solve a sustained state tomography problem. So it's another state tomography problem we defined in this paper. Okay, so here are all the results we have about these three MCSP problems. So we are not going all of them, but later if you are interested, if you want to look at this table, and I can say something about them. But here, if the blue one means that those are results which are easily generalized from the classical result, and for the yellow one, which means that there are results that you need additional techniques in quantum computing to get these results, but they do have quantum analogous results. They do have classical analogous results. And for the red one, which means that they are results unique in the quantum setting. Okay, like the UMCSP is in QCMA, which is unique. And for classical MCSP, we don't have search to decision reduction, and also the reduction between Boolean function to the unitary. And that all these state version results are totally unique in the quantum setting. So let me go to the conclusion. So we study the hardness and applications of quantum MCSP. So we study a Boolean version, the unitary version, and the state version. And all of them, we consider their quantum circuit complexity. And of course, we can consider their classical circuit complexity. And then we also find many interesting connections between this problem and the other problems like cryptography, lower bound, circuit lower bound, and quantum learning. And there are many interesting open questions. Those are just general direction, like the hardness of quantum MCSP, because we don't know whether these problems are like in MP, or can they be MP hard, or can they be QCMA hard, or can they just be some complexity class hard? Yeah. And also, when you consider hardness of quantum MCSP, you should consider quantum reductions or other type of reductions. And we also want to know its relationship between these problems, like whether all these three versions are equivalent, or whether two versions are much harder than the first version. Yeah. And also the connection to other areas. Like here, we do list some of them, but I don't think they are all of them. You must be able to find other applications of quantum MCSP. Yeah. So that's all. Yeah. So if you have any question, just feel free to ask. Yeah.
Okay, thank you for the very nice talk. So does anyone have question or comment? Okay. So when you use the PRG, you say if you can why you use PRG to distinguish the two? Are you saying if you can generate a random circuit that can distinguish random one and the decided function, then you succeed the job?
Yeah.
Okay, so that's
So
the idea.
yeah, that's a basic idea, like because you can distinguish a pseudo-random function that generates from an efficient procedure and a function that is a random function. You can distinguish these two, and then you just distinguish the output of the PRG or the output of a truly random string. Yeah, so like you distinguish the output of a PRG and the truly random string, and you just view them as the Boolean function, the truth table of a Boolean function. Yeah.
Okay, and does the size of T important to your question? Maybe there is some critical point that T larger than something, then the problem is solved, and smaller is not solved, or the
Yeah. Yeah, you are right. So T is an important. Okay, let me go to the. I think I mentioned that here. So if T is smaller than log n, then the problem is easier because you just enumerate all possible circuits to compute the. You just list all the possible circuits, right? And then you just try all of them. If all of them don't work, then you are good. And if one of them good, you are still good. Yeah. So yeah, but if you have more than that, I think we don't have an algorithm to solve the problem right now. Yeah.
So can you say again why the other two is more difficult in some way?
You mean like the problem?
The state and unitary problem.
Yeah.
Why they are harder than the original one, the Boolean one?
So let me go to the. Okay, here. I think here is a good one. So we know that. So first thing is that we know that the original MCSP problem reduced to the UMCSP problem. So because this reduction exists, so we know that UMCSP is at least as hard as MCSP, the gap version of MCSP. So this just gives you evidence that UMCSP could be harder than the MCSP. So it is not. So it's just evidence, not something must be true. And some other evidence is that for these two problems, they have search to decision reduction, and the NP complete problem have this reduction. So these problems are more likely to be NP complete or say NP hard. Okay, but for MCSP, the Boolean function one, we haven't been able to prove a search to decision reduction. So that problem is less likely to be NP hard. So that's another evidence. And also for the self-reduction, the same. SMCSP have the self-reduction, so an NP complete problem have this self-reduction. So SMCSP is more likely to be NP hard, but UMCSP and the Boolean function MQCSP, they don't have this reduction. So probably they are less likely to be NP complete. So that so we don't have like a theoretical proof showing that okay, these two problems must be harder than the Boolean function one, but we do have some evidence showing okay, probably it is true like these two problems are harder. Yeah.
Okay, I see. Thank you.
No problem.
Okay. Any further question or comment? Okay, David.
Oh, I have a question. Yeah. So okay, this is a random question, so I'm not sure if it makes sense. But I wonder if this kind of MCSP problem is it related to proof systems? So what I mean is like is it related to proof complexity? So because one can say other kind of proof system, and it feels like there is also a 2 to the n structure. There's I don't know if there's a relation between these two. Oh, does it make sense?
When you say
so for example,
system, does that mean like PCP or something?
So for example, there are like cutting plane or resolution or like decision tree, those kind of proof systems. So under those proof system, okay, let me try this. So usually if you want to write a proof, you use the logic to write it out. And so there's a question which is kind of like, given a theorem, can I find a proof? So this is kind of the problem in proof complexities. However, like constructing a proof is really hard. Like finding all possible proof is really hard. The space of possible proofs is really large. So sometimes we can restrict the space of proof and ask the same question. So is there a proof in this smaller set that solve the problems? For example, like SOS is also one type, like things like these. And in those settings, you also have this 2 to the n because the proof is usually much longer than the theorem or the statement itself. So I wonder if it's related in some way to this quantum circuit or like circuit size problems.
So I think I got your point. So you are talking about some like programming languages thing, like you have a statement, you want to write down the proof of that statement. So is the size of a statement n? When you say 2 to the n?
Yes, the analogy should be that. Yes, that's kind of the analogy.
Okay. And you say like all the possible proof, the size of proof can be like 2 to the n. You need to try all the 2 to the n strings that can compute they can prove the statement, something like that.
Yeah.
I don't know if people study this, but I think you can define this kind of problem like but another thing is that in the program language you are talking about statement and the proof, and you can it is not standard form in when you translate to language, because language you are considering binary string. But I think it is still meaningful if you consider like, okay, I give you a statement and I give you some size parameter t, and you just ask whether there is a proof with size at the most t. You can define this kind of problem.
Yes, exactly.
Yeah, you can definitely define this kind of problem, and you can try to. But it is hard to say it is in NP or something. But you can try to. I think for this problem, you can have some NP style proof system, like the prover just send a proof, like the proof of a statement to a verifier, and the verifier just run it, and you can check. So probably this problem is in NP in some way, and then I think this is a very interesting direction. You can just consider like if it has some other connections to other problems or something.
Yeah. Because it sounds like if it's related, then maybe you could do a similar thing to extend it to the quantum setting, stuff like that. But I don't know.
Yeah. You can consider quantum. Yeah, I don't know programming language very well, so I don't know. Do you have like quantum proof or something like? For sure, you can consider some quantum statement and then write down the classical proof. But I don't know quantum proof. Yeah.
Yeah, I just searched it. I don't see anything. I only see quantum interactive proof, but it's a different thing.
Yeah, it's a complexity class. I have played that for a while, so yeah, I'm familiar with that one. Okay. That's interesting. Yeah, because actually, like MCSP is just a small part of meta complexity. So meta complexity means that you consider the complexity of complexity. So you can consider that you are given some object like Boolean function or something. You not just consider circuit complexity of it. You can consider communication complexity of the object, the tomography complexity of the object, or like any measure you want to consider about the object. Like you said, like the size of the proof or something, you consider it. So actually, this is called meta complexity, and this is a big object in the TCS. Yeah.
I see. Okay, interesting. Oh, okay. I see.
Yeah.
Okay. I may have final quick question. Is there? Well, can you say more about why the state minimum problem is related to ADS-CFT conjecture? Can you say more?
Yeah. So in the ADS-CFT correspondence, which means that the wormhole, like the picture is that you have a bug and you have a boundary. So there's a ball, and then our world is on the boundary, and the wormhole is something like in the bug, like in the middle of the ball. And in the ADS-CFT correspondence, which means that anything in the bug has a map to something on the boundary. So like wormhole is something in the bug, so there is a map from the wormhole to a quantum state on the CFT on the boundary. Okay, so there's a correspondent. A wormhole corresponds to a quantum state, and then there's a conjecture made by Susskind. He said that the volume of the wormhole is corresponding to the circuit complexity of that quantum state. Okay, so there are many details about like the model or something, but you can just consider that a wormhole, the volume of a wormhole is equal to the circuit complexity of certain quantum state. So the idea is very simple. So you have MCSP algorithm. You just compute the circuit complexity of that state, and after you have late, and also if you can efficiently compute the correspondence between the wormhole and the state, then you can compute the volume of the wormhole. Okay. So that's a general idea. That's a brief idea about like using MCSP to estimate the wormhole volume. Yeah. So, but it conditions lots of conjecture like C equal to V, ADS-CFT, and also the ADS-CFT correspondence needs to be efficiently computable. Yeah, so at least 3 conjectures, and also you need to consider like model issue or something. Yeah.
But the map between wormhole and quantum states is established. Is not a conjecture.
I still think it is a conjecture because ADS-CFT, this correspondence itself is a conjecture.
Okay.
So like some gravity people believe in it, but some other gravity people may not believe in it. Yeah, I don't know if for that community, I don't think that they have consensus on anything. I think for anything they do have something. Some people like it and some people don't like it, and they can approve it. They just have lots of conjecture in the pool. Yeah.
See, thank you. Okay, I think if there's no further question or comments, so thanks Professor Chia again. Thank you.
Thank you. Yeah, thank you for inviting me. Yeah.